Good morning, everyone. My name is Dongguan An. I'm a PhD student at Hanyang University in Seoul, Korea. My research advisor is Professor Simon Song. Today I will talk about the result of our MRV challenge. I will skip the explanation about the MRV challenge. So, our research team carried out this project with the Philips 3T human MRI system. And also we compare the difference between the result that obtained using these two different type of RF coil. The one is a 8-channel knit coil. The other one is a 16-channel torus coil. This is because we normally use the 8-channel knit coils for our experiments, but depending on the size of the FOV, it is necessary to use the 16-channel torus coil instead of 8-channel knit coil. So we want to compare the performance between these two coils. So based on this, we set our research objective to visualize the flow for the MRV challenge and compare the result obtained using different RF coils. So I will describe the experimental setup and post-processing for our experiments. And also I will compare the result obtained using these two coils with the SNR and velocity uncertainty and other flow details. So for the first ones, this is our experimental setup. We use the centrifugal type as our main flow pump, and we use the same injection flow pump and injection hose line with the other teams. And injection flow rate was measured at the right behind of the injection flow pump. And also we use the pressure differential type as our injection flow meters. And also we use the electromagnetic type as our main flow meters. And lastly, we use the 20 millimole copper sulfate aqueous solution as our working fluid. And this whole experimental systems controlled by the DAQ devices to make perfect periodic flow. So using this experimental setup, we performed the preliminary test to check the injection flow rate. And as you can see that the flow rate of the preliminary test slightly different with our desired way. And after many attempts to solve this problem, we determined that this is because the air bubble and the movement of the hose lines. So we try to remove the air bubble from the entire system, and also we pay attention to prevent the new entry of the air bubble. And lastly, we also make the hose line straight and fixed as possible. And this attempt actually works. So our injection flow rate was improved like this, and it was fit more than the preliminary tested with the desired waveform. So this is our MS scan parameters. For two different RF coils, we set the MS scan parameters as same as possible. Especially we set the FANC for the 100 centimeter per sec, and we also set the 0.5 millimeter for our voxel resolutions. And next is post-processing procedure. We apply this post-processing to our MRV data. So for the first one, we configure our scans in order of flow on and off and flow on. After the scans, we subtracted the flow off velocity field from the flow on velocity field to remove the background phase offset. And for the second one, we set the optimal threshold for the slice by slices using the automatic algorithm to make the accurate velocity mask, like this figure. And the last one is we use the wall-bounded divergence-free smoothing filters to reduce the noise in the velocity field, especially in the near wall region like this figure. So from now on, I will show our result of MRV challenge, and for the first one is SNR. We defined the SNR using this reference, and it was calculated by dividing into 3 sections. And for the section 2, the center of the FOV, the 8-channel coil shows a much more higher SNR than the 16-channel torso coil. But in section 1 and 3, both ends of the FOV, they shows the opposing result. This is because the size of the FOV is too larger than the 8-channel coil, so it cannot cover the whole range of the FOV. So it makes the SNR of the 8-channel coil more non-uniform, but for the 16-channel torus coil, it is larger than the 8-channel coil, so it can cover the whole FOV size. So the SNR of the 16-channel torus coil shows the more uniform distribution than the 8-channel coil. And next is velocity uncertainty. We set the definition of velocity uncertainty using the reference of our colleague the Vrushavsky and Grundmann. And also we calculated the velocity uncertainty using the same process with the SNR. And as a result, as you can see, the 8-channel coil shows almost the same pattern with the SNR analysis. But for the 16-channel torso coil, shows not differ much in section 2, unlike the SNR. And also it shows almost a uniform uncertainty distribution for whole section except the section 1 that shows a much better uncertainty than the other regions. So to see the effect of the formal result, we calculate the flow rate of the both coils along in the mainstream-wise directions. And as you can see that the flow rate of both coils shows a slightly overestimated compared to the flow meters. But these two still converge within the plus minus 5% error region. And we can think that the flow rate was very well calculated with the flow meters. However, in this red circle regions, the flow rate of 8-channel coils decreases very rapidly. This is because the 8-channel coil has relatively low SNR and high velocity uncertainty in the both ends of the FOV compared to the 16-channel torso coil. So the flow rate in this circle was calculated very inaccurately. And next is the velocity field. We compare the velocity vectors of these two coils along in the mainstream-wise direction to see how this condition affects in the velocity field. And as a result, at the entrance of FOV, the 8-channel coil shows a high noise in the velocity vector compared to the 16-channel torso coil. But in the center of the FOV, the velocity fields are similar for both coils, and the 8-channel coil shows a slightly better vectors, especially near the wall, compared to the 16-channel torso coil. And to check this result more quantitatively, we set the straight line like this, red and blue line, and plot the velocity profile along them. And as you can see, for most regions, the both coil shows almost a similar velocity profile. But in the x equal minus 10 millimeters, the 8-channel coil shows a highly vibrating velocity profiles due to the high noise. And this can be shown at the peak injection flow rate. And the 16-channel torso coil shows a smooth velocity field than 8-channel coil in the entrance region of FOV. And next we made the iso velocity surface to analyze the effect on the velocity field in 3D region. The surface was constructed by connecting the point with the velocity magnitude equals 4.2 bulk velocity. And we set the 5 slices for the comparison, and the second and third slices shows similar patterns. But the other slices shows slightly different. I'm not sure if This due to the noise or if the velocity field is really different. However, the 16-channel torso coil shows a smoother surface, especially at the end of the FOV, compared to the 8-channel coil. And this makes much more difference. And this observation can be confirmed in the isovorticity surface more clearly. In the red circle, the both ends of the FOV, the many isovorticity surfaces are formed in the 8-channel coil compared to the 16-channel torso coil. This is because the velocity noise are amplified through the differentiation for velocity calculations. So considering this result so far, the 16-channel torso coil can be an excellent choice instead of the 8-channel coil when a large FOV is required. And this is our conclusion, and I will skip this page for our Q&A time. And thank you.